Как видно?
Да.
Какую сюда?
Окей.
Можно начинать?
Yes, please begin.
Okay. I would like to thank organizers for the kind invitation to participate in this nice workshop. It's a pleasure for me to say some words about some works of Maxim and some its possible generalization or extensions. The title of my talk you can see here is the name is Multidimensional Martinez-Solosna-Shabbat-Pavlov Jordan chain and its reductions. High dynamic chains is one of the favorite subjects of studies for Maxim. Okay, the idea of high dynamic chains turned back to Benny, 1973, when in his study of long wave equations, he showed that if instead of dependent variables, we will use their moments, we write them as equivalent form, a system of infinite set of equations, where A, K are moments of dependent variables. This system chain has a number of nice properties studied by many authors, and then it led to investigation of other types of chains done by several authors, some of them mentioned here. Then, at the beginning of 2000, Maxim entered into the game and wrote a paper in Journal of Mathematical Physics entitled Interval High Dynamic Chains. And then he wrote many others concerning the high dynamic chains. But in this paper, among many other results, he showed one very interesting thing. Let's start with this high dynamical type system with very special form of the characteristic velocities represented here, where the epsilon is small is a parameter. And in fact, this type of system called by epsilon system has been considered Maxim even earlier. And now let's introduce the moments defined in the following way. C0, Ck. Remember, here there are n dependent variables. And here, of course, we have only n independent variables Ck. But if we write down now in terms of Ck, this type of epsilon system will end up with the following system of equations, which is infinite system of equations where K run all positive and negative numbers. But now, if we will treat Ck as independent variable, this is really infinite chain done by infinite number of independent variables. This is Pavlov chain. He discussed some properties of this chain, reduction, connection with other system, and so on. This type of chain appeared later in quite different setting. In the consideration of so-called confluences of hypergeometric functions and their connections with the interval dynamic type systems. In fact, is the most degenerate case of this confluence of hypergeometric functions, one ends up with the following type of systems. For two components is the following system of, for two variables u1, u2 in 1 + 1 dimension. For arbitrary n, we have the following system, again, with 1 + 1 variables. And you can see easily that matrices here, Z1 and Z1 are just standard Jordan block with all consigned eigenvalues, simplest one. Okay, now if we form this system of equation integral, it can be solved by holograph method, but clearly this type of system doesn't admit the introduction of the Riemann invariance. This is not obviously not diagonalizable. If we now consider the formal limit of this system of equations, and when n goes to infinity, we end up with the following chain. It's one-dimensional. We call it Jordan chain. But then, after completing that and taking a look back for 15 years, we understood, okay, this is no more, no less than exactly the Pavlov chain with the following connection between Ck and Uk for positive K. Of course, the introduction was completely different, but never the same chain. Moreover, Pavlov chain or that Jordan chain appeared early again in different settings in earlier paper of Martinez Alonso and Shabbat, when they discussed so-called universal high dynamic type hierarchy, hierarchy written in the following way, where capital Y is a Lorentz series, AI is this positive part of this product, this bracket is defined here, and you have infinite set of chains. The first member of this member of this hierarchy is presented here. Looks different. It can be called Martinez-Alonso-Sabat chain, but nevertheless, this chain is just equivalent to Jordan chain, and the equivalence is given here. Yn is just equal. If you can start with the Jordan chain with dependent variables U1, U2, and so on, and then consider the so-called elementary Schur polynomials defined by this standard formula, where Pn a function of all UK, then variable Un introduced in such a way to solve the Martinez-Alonso-Sabat chain. So Pavlov chain, Martinez-Alonso-Sabat chain, Jordan chain, in fact, the same chain, just written in different variables. Okay, as written here, it can be seen, can be thought as, okay, one more chain, so what? Nevertheless, this chain has a number of interesting properties. And first, let's consider the hierarchy of this Jordan chain hierarchy. It can be written in the following way, where Pm k plus m minus l, again, elementary Schur polynomials. Okay, it can be written in such a way. Let's take the first two equations, first equation, this time T1 and T2. Then, if we eliminate U3, we'll end up with the following two equations, which implies immediately existence of function phi given here, and this function phi obeys the following single equation in 2 + 1 dimensions. This in fact coincides with Mikhailov equation found much earlier, and this fact of appearance Mikhailov equation as a particular case of the Jordan chain hierarchy or Pavlov hierarchy has been mentioned by Maxim in just recent paper. First result, then, in fact, Jordan chain appear in other aspects. It can be viewed, and in fact, it is the way to regularize gradient catastrophes for the Burgershoff equation. Okay, the observation shortly is the following. Let's start with the Burgershoff equation, or Riemann equation, call it as you like, of that type. And we know very well there are problems with the blow-up of derivatives of gradient catastrophes, and sometimes some coordinates, derivatives blow up, becomes infinite, and of course there is a problem with regularization. And in this paper, the way to regularize is called parabolic regularization has been proposed. Let's try to remain within the parabolic type systems in a way which can be called a minimal way. Just do not introduce additional characteristic speed or characteristic parameters. So let's pass from the Burgershoff equation to the following system of two equations. And this is exactly two component Jordan system I presented before. Now we have two variables U1, U2, Jordan block here. This system is solvable. Solution can be implicitly constructed by the Konopelchenko equation, and so on and so forth. Observation is that if you will consider the hierarchy of blow-ups for the Burgershoff equation and just embed this Burgershoff equation into this two-component Jordan system, first order blow-up of first level from this disappear, doesn't show up in this system. Second order, high orders remain, but first order just disappear. So one can say that in this embedding, from the first order gradient, first order blow-ups is regularized. Of course, this system of equation again has blow-ups of derivatives and gradient catastrophes, and one can and it was shown that it can be regularized by embedding into the three-component Jordan system. But again, there are other higher gradient catastrophes for the three-component Jordan system. We can regularize them proceeding to the four components and so on and so forth. If you would like to regularize all gradient catastrophes for the Birgershoff equation of all possible orders in the so-called Poincare case, we will end up with a Jordan chain. In other words, embedding of the Birgershoff equation into the Jordan chain allow us to regularize a very specific so-called parabolic way, regularize all gradient catastrophe of this equation. And in fact, this regularization can be in different ways. One way of to see it as a sort of averaging process with generalized area distribution. Okay, one property of the Jordan chain, and it shows that okay, it may have sense even even for problems of the regularization. Moreover, Jordan chain has a number of other nice properties. Let's consider the first two equations for the Jordan chain or Pavlov chain or Martinez-Alonso-Shabat chain. Let's impose the following constraints of the variables. Remember, here we have infinite set of dependent variables, U1, U2, U3, and so up to infinity. If you impose the following constraint, where nu is arbitrary parameter, the first equation, obviously, is reduced to the following equation, and is no more, no less the Burgers equation in one dimension. Moreover, if you will take a look on the second equation, this equation, in fact, defines completely and explicitly U3 in terms of U1, in terms of the solution of the Burgers equation. Also, U4, U5, all of them will be so-called differential polynomials. In fact, this reduction of the Jordan chain to the Martinez-Alonso-Shabat chain to Burgers has been observed for the first time, Martinez, Alonso, and Shabat. Moreover, one can show that the Jordan chain hierarchy is reduced to the Burger hierarchy. Okay, let's write down the first equation for U1 for the Jordan chain in the following form, where again K plus 1 elementary short polynomial. And now again consider the following constraint we discussed before. It is easy to show that short polynomials under this reduction assume the following form with the following operator, and this hierarchical equation for K run from 1 to infinity assumes the following form. And this is exactly the Burgers hierarchy, and this operator represented here is well-known recursion operator for the Burgers hierarchy. So what we can say, so if we take solutions of the Jordan chain, impose these constraints, this subclass of solutions, we will get solution of Burgers equation. Vice versa. If we take any solution of Burgers equation, okay, define and U1 will be solution of Burgers equation, define U2 in the following way, and U3 and 4 by a relation given on the previous slide, we'll end up with the solution of the Jordan chain. Well, even more, one can show the Jordan chain means the reduction for KdV equation. Again, it was mentioned for the first time by Martinez, Alonso, and Shabat. Indeed, let's consider now the following constraint, where U2 is a second of the contains the second of the derivatives of U1. The first equation of Jordan chain assumes the form of this form, the KdV equation, and again, higher variables for Jordan chain, U2, U3 becomes the differential polynomials of certain time. Moreover, one can show that elementary student polynomials assume the following form, where operator R is given here. One can easily recognize a very well-known recursion operator for the KdV hierarchy. So this hierarchy of equation from the Jordan chain assumes the form of the hierarchy of the KdV equations, where capital R is a recursion operator for the KdV hierarchy. And one can show many other relations. For instance, from the previous formulas for Jordan chain under these reactions, one can easily see connection with the resolvent for the KDB hierarchy discussed long time ago and defined in GDEq. And again, if we take a solution of the Jordan chain, impose this constraint of the previous slide, this constraint, we obtain the solution of KDB equation. In opposite direction, if we will start with the solution of the KDB equation for U1, define U2, U3, and so on and so forth, by these formulas, we obtain solution of the Jordan chain. So we can see that Jordan chain, or Martin-Solonitz-Shabbat Pavlov's Jordan chain, is rather rich. In a sense, it has number of properties, some applications, and contains many equations which are from the point of view of KDB, nothing to do with dispersion-based, nothing to do with dynamic type systems. But nevertheless, they are inside the Jordan chain. So now we have the quite natural question, okay, what happens? Can we proceed? Can we extend all that to higher dimensions? Well, let's recall that and proceed in a way. First, we will consider Jordan systems at its extension to higher dimension, and then we'll pass to Jordan multidimensional Jordan chain. Okay, Jordan system, n-component Jordan system in one dimension is given here for n equal 2, 3, and so on and so forth. For n equal 1, it's just nothing, no more or less the Burgersdorff equation, and it's old, long-known classical textbook example. It can be solved by using the following Hadograph equations. Okay. Now, result which I would like to present here is that the n-dimensional extension of this Jordan system is of the following form, where we have finite number of variables, I'm sorry, u, l, n plus I, where I run from 1 to n is dimension, and l run from 0 to n minus 1. This is just analog, any dimension analog of this equation of Z1 and Z1 of this one. For n equal 1 component, this Jordan system is exactly the so-called homogeneous Euler equation in n dimension. I mean by homogeneous Euler equation, standard, important equation for hydrodynamics, call it Euler equation or Navier-Stokes equation. In the case, in situation when we can neglect all effects on viscosity, pressure, and so forth. So we have 0 on the right-hand side. And in fact, it was long known, back to works of Zildovich, Farana, Feyerabend, that it can be solved by the following set of Hadograph equations implicitly. Okay, now we will try to understand some properties of the n-dimensional Jordan system. All right, we start with the following Hadograph equation. Now, doing in standard way differentiation with respect to variable x, coordinates, and time, we will end up with the following relation, where a matrix element of the matrix capital A are given here, where matrix omega is very special, and we have one on the line and have a small block in the upper left block here. If you do differentiation with respect to t, we end up with a following relation. Now, if where v is the following vector, we introduce it for convenience. So if determinant of matrix A presented in the previous slide is different from 0, we can invert this and we end up with the following relation expression for derivatives. And now it's quite easy to see that multiplying this relation by uk, we end up with the following system of equation. Now we have the very nice form written explicitly, but here we have the elements of matrix A minus 1. Now let's impose the following constraint presented here and there. And under this constraint, this system of equation takes the form of the n-component Jordan system presented before. Of course, this relation between elements of matrix A-1 and derivatives is not trivial. They are equivalent to the following constraints of the elements of matrix A. And remember that matrix A is done by the derivatives of the functions f with respect to dependent variables. And of course, the elements of matrix A-1 are constructed like that. So this is in fact the system of equation for this set of functions. But important that a number of constraints here coincide with the number of the dependent variable. So this system is not overdetermined. So any each solution of this constraint provides us using the methodology equation solution of the n-component Jordan system. Okay, there is another form of the equivalent form of the Hodor equation presented here. I will not discuss it. And there is connection with the theory of maps. I will leave it. Yeah. Okay, and here there are some examples of this Jordan system in 2 and 3 dimensions. Okay, in 1 dimension, it is of the following form. In 2 dimensions, the system with 4 components with the following matrices presented here, Jordan blocks of special form. In 3 dimensions, the system of 6 components with the following 3 terms with these matrices presented here. And these matrices have all rather pretty good properties. All of them are Jordan type blocks. All of them are not diagonalizable, but moreover, this matrix, oh, I'm sorry, I should go back. These 2 matrices commute between each other. And all these 3 matrices commute between each other too. And it's continuous for arbitrary n. So these Jordan matrix systems in n dimension are constructed in a very special way. And I would like just to know this difference with the naive choice of Jordan blocks in, for instance, in 2 dimensions. Okay, how we can see all this Jordan system in the same way as it was in 1-dimensional case about parabolic regularization. For n equal 1, we have the homogeneous order equation given here. Okay, it has number of applications, in fact. It can be solved by the following Hodor equation, blah, blah, blah. There is matrix M presented here, and the blow-ups of derivatives of gradient catastrophe for homogeneous equation happens on this hypersurface given by the conditions determined of advantage. And the properties of this thing have been described by different authors, for instance, by Zhenya Kuznetsov 20 years ago, by Giovanni Artenzi and myself. And in fact, one can show that blow-ups and gradient catastrophes for the n-dimensional homogeneous order equation has another rich structure, fine structure on the first level, boundedness of derivatives, and so on and so forth. I will not discuss all that here. But how to regularize all this gradient catastrophe? In fact, one can do the same thing as it was done in 1 dimension. Let's pass from the Jordan homogeneous order equation to 2-component Jordan system, where derivatives are given by the following form: matrix A for n equal 2 is ever, where in this angle we have the matrix A which corresponds to the homogeneous order equation for n equal 1. Of course, okay, that derivatives for homogeneous order equation blow-ups when determinant of this matrix vanish. But for n equal 2, the vanishing of this determinant doesn't apply in general. The determinant of this matrix vanish. So embedding of the homogeneous order equation in 2-component Jordan system in n dimensions somehow regularize gradient catastrophe for homogeneous order equation. Or at least one can show on the first level. So one can proceed from n to n equal 2, then to n equals 3, n equals 4, and one should expect, and it can be almost can be shown, that embedding the homogeneous order equation for the Jordan system is arbitrary, and we can regularize the set of the gradient catastrophes and blow-ups for the homogeneous order equation. It has been discussed in the paper. Okay, now this indicates that consideration of the Jordan system in the formal limit n goes to infinity would be quite useful. Okay, and this is the form of Jordan system in n-dimension, a Jordan chain in n-dimensional case, where index I runs from 1 to n, and n runs from 0 to infinity. And again, one can write down the homomorphic equation, infinite set, not that simple to treat, not that clear what does it mean, but nevertheless. And now, by analogy with the one-dimensional case, it's quite obvious and quite natural to consider different types of reductions. Let's start with the following constraint, where derivative of un plus I with derivative with respect xi, there is no summation over I here, is given here, where rho is density function obeys the following continuity equation. P is a function, we'll call it pressure. This is just a Laplacian, and nu and xi are constants. Okay? Under this constraint, the first equation for L equal 0 from the Jordan chain becomes the following equation. And this is no more, no less than n-dimensional Navier-Stokes equation. In n equals 3, I just change a little bit notation for xi just to eliminate the combination at xi with some coefficients. Okay. What about the other equation for Jordan chain? The same way as in one dimension, one can show that all other equations serve as a sort of recurrent relations to calculate all higher u, l, n plus I for L equal 2, 3, and so on and so forth in terms of solutions of the Navier-Stokes equation. Corresponding constraints for the matrix A, which is infinite dimensional, have the following not pretty simple form. Nevertheless, any solution, if one can find it, of the system equation which correspond to the system differential equation for the function f, one can construct solutions of the Navier-Stokes equation. How to do this effectively, or it can be done in reality, is a very good question. In opposite direction, if we take any solution of the Navier-Stokes equation presented here, any dimension, define u n plus I by the following relation, then all higher L, UL plus 1, N plus I by the following recurrent relation, we will construct the solution of n-dimensional Jordan chain. Okay, there are other reductions. Let's choose the constants nu and xi equal to 0. There is no viscosity. Fluid is inviscid. Then we end up with the earlier equation. If we would like to impose the constraints that the fluid is incompressible, so the divergence on V is equal to 0, we will obtain this case, impose the following constraint. This, of course, implies constraints on the pressure of the following form, and we end up with the following earlier equation. Constraints for A are rather simple, simpler than for Navier-Stokes equation. Well, let's proceed. Now let's consider the following constraint, where nu is a constant, nabla is Laplacian. The first equation of Jordan chain becomes the n-dimensional Burger's equation, which is well known, have a number of applications, discuss a number of papers, for instance, this recent review. Constraint for the matrix A is presented here. Well, now let's consider quite different reduction. Okay, let's introduce the following parameterization of our infinite set of dependent variables for the Jordan chain in the following form, where VIA are our new dependent variables. Epsilon I are arbitrary constants. M, capital M, is arbitrary. So we have certain set of new dependent variables. Here we'll have infinite set of dependent variables. Here is a finite set. Substituting this parameterization, this equation into the Jordan chain equation, we end up with the following relation. This implies that alpha obeys the following set of equation, where lambda presented here. And this is in fact the n-dimensional relation of the one-dimensional epsilon system considered by Pavlov more than 20 years ago. Indeed, if we consider n equal 1, this is exactly the expression for characteristic speeds, which appears as a study of the epsilon systems. Remember that alpha here runs from 1 to m, capital M, where capital M is arbitrary. Okay, so one can use this relation in different ways. If we will be able to solve this multidimensional epsilon system, we will be able to construct the solution of Durgan's equation, and in fact, in principle, solution of the Navier-Stokes equation by the formalization. Of course, in the middle, we should solve the following constraints, and this is really difficult to say about the effectiveness of this procedure. But nevertheless, there is this type of relation. One can proceed. Okay, in fact, it would be interesting to see about what happened with this multidimensional epsilon system. For n equal to arbitrary m, this system has the following form. Is the simplest possible way for one component, so two components in fact will be. In two-dimensional, this epsilon system has the following form. And in fact, one can try to find a way to solve it, or by the use of sort of extension, generalization of Khodogrov method, any other question. But up to now, it's still an open question. Well, one can do other constraint, consider other constraint, to obtain other equation which we know very well. So again, this is the first equation from the Jordan chain. If you impose the following constraints of the un plus I, we'll end up with the following equation. And it's an n-dimensional system of equations, but very strange, or very particular, better to say, dispersion law. For n equal 1, it's just KdV equation. Moreover, if you consider this system of equation and impose the following constraint, then for U1 we obtain the following n-dimensional equation. Remains that Laplacian contains n variable. So it will be n-dimensional equation with sort of generalization of KdV equation. Okay, let's proceed. Consider more complicated constraint. We will end up with the following system of equations. If then we impose the following constraint, and where delta I now is a sort of Laplacian, where variable I does not participate, we will end up with the following system of equation. It contains of differential effects. If we now impose the constraint U2 is 3un equal to 0, we will end up with the following single equation, which is known as the dispersionless KP equation discussed by several authors. Well, now, of course, it would be, if continue to get other equation, and I will present here, okay, I think I do not have a lot of time, a reduction to the KP equation. Indeed, if we impose the following constraint, we will end up with the following equation. And under this constraint, we end up with the following single equation with parameters alpha and beta. This is for n equal to, this is exactly Konopelchenko equation. Okay, and then one consider other extension for two dimension, more complicated in a different way. Well, okay. One can discuss other type of constraint, and one can see easily that one can get a lot. In fact, Jordan chain in n dimension contains number of different equations of different types, of different properties, and under the different type of reductions. Well, and of course now there are a number of questions which can be addressed to all of that. Of effectiveness and what to do with this reduction, what does it mean, what about the hierarchy of what happened with the hierarchy of the equations. All these problems are completely open. But there is some way to extend all that. I would like to mention the recent paper by Lindgren and Ferapontov, when in fact they showed that in this paper, in this talk, I discussed just journal blocks as extremely simple, or more simple form. But one can extend it considering journal blocks of more general form, like Toplic match and so on and so forth. And they showed, in fact, in this way, one can end up with sort of modified KP hierarchy. Well, then one can also consider a more general case when instead of UK you have the arbitrary function and so on, so forth. So one can proceed in different directions and ask different questions. And most probably, I believe, Maxim is the right person to ask what does it mean and what could be done. Unfortunately, I never collaborated with Maxim in all the many years we know each other. We met many times in different places. In probably one of them is just the south of Italy, which Maxim liked very much. And this is one of the photos of him, I believe, somewhere on the tip of the Italian boot. First photo. Second with Zhenya Ferapontov. Even she looks different, nevertheless the same thing. Then this is a photo of Maxim during the one conference in Gallipoli, in Syrinuze. And you see, and Maxim always is looks very seriously. He always think about the serious problems. And in fact, it happened many times that I asked Maxim to help me to clarify several things. And probably this photo, again, the same place. I just show that Maxim is always watching you very carefully. What you are asking, what is your question? And I'm absolutely sure if somebody or myself, and I would like to do this, will ask Maxim, what does it mean all that? What does it have sense? How one should proceed? Where it will lead? Maxim will say shortly, oh, well, it should be like that. Thank you. So I just want to say, дорогой Максим, я вас поздравляю, and all the best from all your friends, including many friends in Italy. That's all. Thank you very much. Thank you for your attention.
But it was very interesting, and I join your congratulations. Okay, does anyone want to add something, to say something to Max, or to ask questions to Boris? No?
Yes, I have a question.
Yeah, okay.
Boris, you presented lots of equations derived from this Jordan chain, some of them integrable, some of them apparently not. Is there anything one can conclude that these equations inherit from the Jordan chain? Are there insights on the level of the Jordan chain which you can take over to all those equations which you presented us?
Oh, I do not know how to answer correctly. As I said, it's a sort of, I didn't mention this result about multi-dimensional Jordan chain, very recent results. And of course, all of them are open questions. And what all these reductions means, for instance, from the point of view of some special properties, is still open. For instance, even in one dimensions, and this we discussed recently with Yuji Kadama, as I mentioned, to take the one-dimensional Jordan chain, this reduction to the Burger's equation for KdV, Burger's hierarchy, KdV hierarchy. And in all these cases, in fact, the all higher variables become the differential polynomials. Is this special property or not? What does it mean? What does it mean from the point of view of integrability or Hamiltonian structure? Or I have no answer at the moment. And moreover, even in n dimension, I almost have no answers yet. Even the first question, what about the hierarchy of the multidimensional Jordan chains? No answer at the moment. If it could be found, it would be very rather interesting, I believe. But I have no answer. I'm sorry.
Okay, thanks a lot for this nice talk.
Thank you. More questions?
I have a question. If this Jordan chain, then solution involve exponent and power of t.
Sorry, I didn't understand the question. Repeat, please.
Because the equation has like Jordan matrix.
Yeah.
Then solution probably will involve exponent of t and power of t. T1, t square, etc. Yeah.
No. Why? No, even for homogeneous order equations, there are solutions which behave a quite different way. And for Jordan chain too, it should not grow exponentially, no.
But here eigenvalue has кратность, я не помню, кратность больше, чем 1.
Again, I cannot hear well. So what is greater than 1?
Кратность.
Кратные?
Ну, собственное значение будет не одно собственное, а кратность больше, чем 1.
Well, okay, that's a good question. I don't know. In fact, the structure of the space of solution, of manifold, a variety of solutions for n-dimensional case is not investigated really. In fact, what we did recently, we just tried to understand what is going on with the blow-ups of derivatives of gradient catastrophes. What could be the classes of solution with such special properties? No, we have no answer, fortunately.
I see. Thank you.
Okay, thanks. More questions? No questions? Yes, of course. So, Max? Your turn.
Okay. Thanks everybody who was able to participate in this meeting. Thank you, everybody. I'm happy to that you join us. Now we are going to restaurant and we will celebrate this possibility to meet now. Thank you. Thank you, Boris, for your talk, and thank you for Folkert and Dmitry Millionschikov. Thank you.
Спасибо. В какой ресторан идете?
Да.
Присоединяйтесь.
Я очень присоединяюсь.
Okay, everyone is invited to join us. Okay, thanks a lot. I think it was a nice...
Iosif,
Да, Жень, конечно.
just a few words from Lavbora.
Yeah.
We are here with Boris Kruglikov, with Boris
Yes.
Kruglikov, watching
Yes, we see
the
you.
conference. And we would like to congratulate Max once again. So I know Max for more than 40 years as a great colleague, as a friend. And okay, it was, I have benefited enormously from his expertise in mathematical physics,
Yeah,
from
I agree.
his ability to see connections, to offer nice problems, to ask good questions. We have 11 papers together, I counted today, so I hope we will continue. And we will join, we will certainly raise glasses with Boris. We can't join you to the restaurant. It's a pity, but we will raise glasses today.
Okay, thanks. And I want
Thank
to,
you very much.
Черт возьми, что не говорите, куда идете?
Да здесь рядышком грузинский ресторан. I
Как-
want to remark that Zhenya and Raf Vitala helped a lot to
Yes,
arrange.
I am here.
this. Yeah, I know that you are here. So thank you very much for your help. And I think that, well, our enterprise was quite successful. Well, thanks a lot. So this is the last but one session in this year. We meet next Wednesday and they go to holidays till February. Well, just in case, Merry Christmas, Happy New Year, but I hope that we'll have a chance to...
Вот черти, не говорят, в какой ресторан.
Говорю, почему?
Какой?
Congratulations, Maxim.
Здесь такой, есть
Самый
такой
вкусный
грузинский
ресторан.
ресторанчик неподалеку, Эларджи называется.
Как называется, все равно непонятно.
Эларджи.
Ларджи?
Эларджи,
Ларджи.
да.
Ага.
Мы можем оттуда устроить вам видеосессию, когда придем. Окей, thanks. See you next Wednesday. Bye-bye.
Bye.
Ладно.
Рад, Женя, вас увидеть обоих. Извините.